All right, so yeah, we're interested in, so how do we evaluate a double integral? What is the procedure here? Well, let me just show you one particular one, and then we'll talk about there's another option too. Okay, so to do a double integral, one way to do it is like this. All right, so let me just put in some upper and lower limits here. So I've got C to D on one of them, A to B on the other. So here's how we're going to evaluate this double integral that we solved was the volume under a three-dimensional shape between the z value and the xy plane. This is one way to do it. All right. So here's what I've got. I've got two integrals. All right, and then what you do is you look at kind of the innermost first. Okay, so the innermost one I have here is I've got an integral from A to B of this fxy dx. What that means is I'm going to integrate with respect to x, integrate with respect to x. And when I do that, since I'm integrating with respect to x, I'm going to hold the y value fixed, like we did with the partial derivatives. So I'm going to hold the y value fixed. I'm going to integrate it with respect to x. So we do the innermost first. All right? Well, once I do that, so I've got this function in two variables. I'm holding the y fixed, though, and integrating with respect to x, which, that can lead to all sorts of things, power rule, u substitution, the drill. All sorts of things we can run into there. All right? So once I have that then, what that'll turn out then is that's going to be, I'll tell you what, let's just do one and show you what we mean here as we go along. Let's say I've got the double integral over this rectangular region R, and the function is 4 minus y minus x dA. And the R, I'm going to run that from 0 to 2 by 0, 1. Again, those are usually the x's are given first, the y's. So by my explanation here, what we've got is this integral here. All right, so the x's, if I do the x's first, the x's are going to run, this will be my A and B. This will be my C to D. And so the x is going to run 0 to 2 of this 4 minus x minus y. And then the y's go on the other integral limits of it, so the y's are going 0 to 1. So what I'm saying is here, I'm going to do the innermost first here. Integrate that with respect to x, treating the y as a constant. So if I integrate this with respect to x, this function here, well, I'm doing antiderivative. We talked about partial derivatives. Well, now we're going to do partial antiderivatives, I guess, one way we could phrase it. So this, integrate that with respect to x. So the antiderivative, if I'm holding the y value fixed, integrating with respect to x, that would be 4x. I'm doing antiderivative now. That would be 1/2 x squared minus. And then what about this y? Well, it's fixed. It's just like the 4 was, right? Y is fixed. So what would be the antiderivative with respect to x of that? It's yx, right? And so that's running from x is 0 to x is 2. So you see what we mean here, what this is interpreted as. One way to interpret it is integrate that with respect to x first. Just like we've done in the past. Now we just have the y thrown in there too, but kind of get the general idea here of what this means. All right, well, yeah. Now we've got x is 0 to x is 2, so we're just going to plug those in. We've still got this integral 0 to 1 to deal with, but all right, so if x is 2, I've got what, 8 minus half of 4, so that'd be 8 minus 2, minus that would be 2y. And then plug in the 0, that's nice because all those are zeros. So what we wind up with usually is now we have a function left, but it's only in terms of y. What is it, 6 minus 2y? With me there? Okay. Well, now that's more like we've encountered before. We know what to do with that, hopefully. This is now just a simple little one variable integral. We're doing it with respect to y, so what are we going to get? 6y minus y squared, but we're going to divide by 2, so it'll just be minus y squared, wouldn't it? And then evaluate that 0 to 1. So yeah, when we do this first integration, what that leads us to then is an integral with respect to the y. And we finish that off doing our antiderivative things that we know how to do. Hopefully you remember how to do anyway. Plug the 1 in and the 0. 5? That's what I get anyway. Not too bad. Not too bad. Now, just to remind ourselves, so what is the 5? What does it represent? It's a volume, right? And what volume does it represent? Well, it'd be the volume of this function right here. Let's say from z equals 4 minus x minus y to the xy plane, let's say it this way, the volume between z equals 4 minus x to the xy plane over this R region. Now, one slight little thing to keep in mind. You know, the example I did, that volume that we found, we were talking about, you know, the volume was, I didn't draw it out, but I definitely had, go back to it, I didn't draw it out, but it was all above the XY plane. So it was this kind of cone shape, I guess, but it was always above. So that volume, you know, it's all going to be positive. What would happen if it goes below the XY plane? What do you think would happen? Well, what happened when I had, say I had this from A to B? When I did the integral A to B f of x dx, what happened? The area I found was actually a net area, wasn't it? It was this area minus this area, right? Same thing happens over here. If your z values drop below the xy plane, it's going to compensate. You're going to have the part on top minus the part below the xy plane. So it's a net volume. When we say volume, like here we sometimes just say area, but it's a net volume. Okay, you know what I'm saying? Because the part below would be subtract the part above minus the part below. So anyway, just thought I'd throw that in there. But what you're finding is a volume between this shape, three-dimensional shape, and the xy plane over this rectangular, in this case rectangular region. Okay, kind of keep that. All right, now. Also, though, all right, going back to this, what do you think this means? If I want to evaluate this, what if I do A to B, and then C to D, f of x, y, dy, dx? What's the difference there? Again, you do the innermost first, or the integral to the right first. So what's the difference here? What am I integrating with respect to first here?
Y.
Integrating with respect to y first. Then you do the x's. Yeah. So we integrate, in this case, we integrate with respect to the y's first. Then we'll do the x's, and we're going to keep the x's fixed. Of course, when you do that, but you do those y's first. Okay? Now, good news. Here is a theorem. There's a theorem that links these two. And the good news is, Dubini's theorem. Here's Dubini's. If f of xy is continuous on r equals ab by cd, x's are a to b, y's are c to d. If it's continuous over that, then the integral, the double integral over r of f of xy dA equals the integral a to b and then c to d, f of xy, let's see, that would be the y's first, dx. But that also equals the integral c to d, integral a to b, f of xy, and that's the x's first, then the y's. Dubini's theorem says it doesn't matter. You can do it either way. And you get the same exact values. Okay, so let me just show you that is true here. Let's just do one to verify that these are the same. So show that the double integral over r, 100 minus 6x squared y dA, where r is x go between 0 and 2, so we'll sometimes write the limits this way, same thing, is the same either way as value. In other words, we're going to show this to be the case. do both ways. All right, so let's see. Let's do 0 to 2 for the x's, and then -1 to 1 for the y's. So that's the y's first, and then the x's. All right, so what would it be if I do the y's first? So I'm doing this first. 100y minus, so I'm integrating with respect to y, so that would be 6x squared, and then the y's would be 1/2 y squared. Again, doing the antiderivative now. And then we're doing that -1 to 1, then we'll do the x's next here. Okay, so it's -1 to 1. I think I'm doing it the hard way first. Maybe not. All right, so that'd be 0 to 2. Plug in the y to be 1, so that'd be 100. So that'd be 3. Now, this is y values, so I'm going to plug in for the y, this one in for the y, so I have 3x squared times 1 squared, so that's just 3x squared. Then I plug in the -1, so that'd be a -100 minus 3x squared, but -1 squared is still 1. So that's going to give me interval 0 to 2. What is that going to be? 200. And the x squareds cancel out. Minus make it plus. I think so. Okay. Just 200, and then 200, which makes it easy. Just 200x. Now I'm integrating with respect to x, so that's just 200x. 0 to 2, that's going to be 400. If we do it the other way, okay, so the other way I'd do the x's first, so it would be -1 to 1, then 0 to 2. The x's would go inside here. Then it's 100 minus 6x squared y dx, then dy. So I would do the x's first, so what is that? -1 to 1. So x's, so 100x minus the x cubed, so divide by 3, so it'll be minus 2x cubed y. And that's for x equals 0 to 2. So that's -1 to 1, plug in the x to be 2, so that'll be 200 minus 2 times 8. So it'll be minus 16y. And then the good news is x is 0 gives me zeros. So I'm down to this. Now I'll integrate that with respect to y. So it's 200y minus, what, 8y squared. So that's -1 to 1. So that's 200 minus 8 minus -200. And then minus 8 again. So it'll be 200 plus 200, and then -8 plus 8. This one. So, okay, so yeah. Rubini's theorem doesn't matter. All right.